Chapter 7, Section 7.4 to 7.6, multiple regression. So we're going to look at multiple regression and we'll look at a few examples here. And we're going to start off by the multiple regression model. And this is what a multiple regression model means. Multiple regression model looks very similar to the linear regression model. If you recall that the linear regression model basically didn't have this stuff in it. That stuff was missed out of it. That was the main difference between it. So we didn't have any of this stuff. And we just had the remaining stuff in the model. And it's a very similar idea as we're extending the idea to have more independent variables. As before, that error term or that epsilon, that Greek letter, just corresponds to the change in y, the dependent variable, that cannot be explained by the independent variable. So moving on to the next slide. So what do these coefficients or slope means? These slopes, beta 1, beta 2, let's just generically call them beta I. So the slope beta I is a change in the mean value of the dependent variable y, corresponding to a 1 unit increase in the independent variable x. And that's when you hold values of all other independent variables constant. I'll do an example of that as we move on shortly, so you can actually see what that actually corresponds to. So move on to here. And so the estimated multiple regression equation looks like this. So basically what we've done here, the difference here is that we're using B rather than beta, and all that means is that we've just acknowledging that we don't have population data and we're using samples to derive our estimated multiple regression line. And we have the same graphic as we had before. We start off over here with our original multiple regression model, and it's got betas in there. It's got the betas in here and the error term. If we had population data, that would be great. We'd be able to maybe figure that out. But what we typically don't, so we take our sample data. From our sample data, we develop coefficients. Instead of betas, we've got b's, and that actually leads us to our estimated multiple regression model. So what I'd like to do now is actually go back to the linear regression model very briefly and remind ourselves of what we had before. And what we had before was butler tracking, and this is the information we had. So let me just come here and say, remind ourselves, what did we say that which one was the dependent variable? I think the dependent variable was the time, and the dependent variable is going to actually take the symbol y, because the time it takes to complete your deliveries is going to be dependent on the miles you drive. So let's put the miles over here as x as the independent variable, and what I want to do is run that in data analysis. So let's got data here, data analysis over here, and I want to get the linear regression model. And so we're going to hit regression. You may have old data in here from work you did before. You can just get rid of that. So the input y range is going to be this, and the input x range, make sure you don't switch these over. Make sure you don't. Labels are included, and let's put the output in cell E1. That's good, and let's get the answers to that. So what we've got here is three main things. Let's have a look at them in turn. So we've got the R squared, telling us how good the model is overall. R squared coefficient determination is in fact telling us the amount of deviation in the dependent variable that is brought about by deviation in the independent variable. So in this case, it's saying us the amount of deviation or change in the time it takes to complete your journey that's brought about by deviation or changes in the mileage that you drive. And it's rating it at 66%. It could be as high as 100%. So what that means is that the model is okay, but there's other factors that are influencing the time it takes for you to complete your your deliveries. Okay. In fact, there's other factors accounting for nearly 34%. The difference between 66 and 100 is about 34. So there's about other factors that account for 34% of the time it takes you to make your deliveries, other than just the time. And we have the intercept and the slope down here. So based on those, we can actually use those figures to actually derive a model. And the model is going to look something like this. Let's just draw it in. So the model for the amount of time it takes to make your deliveries, let's see, is going to be linear is y hat equals b0 plus b1x. And then that hat thing in there means estimated. And for us, y is time. So the estimated time to make your deliveries is equals to b0. And b0 is 1.273913 plus the slope, which is 0.06. I'm just getting these from up here. 0.67826. And we're going to multiply that by x. And what was x for us? X was the miles. So we're going to multiply that by the number of miles. So this is our regression model that we can use for estimation purposes. So I can actually estimate the time somebody that, say, for example, is going to drive 100 miles. All I do is put 100 in here, do this calculation, and I find the estimated time. In fact, I'm going to just do that here. Let's get onto somewhere. Let's just do it right here. So the estimated time for someone who's going to drive 100 miles is going to be equal to 1.273913 plus 0.67 multiplied by 100. So the estimated time is going to be 8 hours and 8.05 hours. And the slope, I just mentioned what the slope is again. The slope in here is 0.67. What the slope means is this. I'll do calculations for you up here. Let's look at the estimated time. So the estimated time to drive, say, well, have a certain amount of miles. So what's the estimated time to drive, say, 100 miles? We was the same calculation we did below, so I'm going to just say it's going to be equal to this guy. I'm going to press F4 because I'm going to actually copy this calculation down. F4, it just puts dollar signs in front of my F and the 17, which means as I copy the cell, as I copy this formula down, it's still going to refer to this cell in here. So then I'm going to add in the miles, F4, and I'm going to multiply that by whatever the 100 in this case, where I've got up in this cell here. And so I can move that up. And I just have to adjust that because Excel doesn't want to play. So it's not K4, it's going to be K3. Okay, so that's what you have right there. If someone drives 100 miles, then you are going to estimate their time to complete those 100 miles is actually going to be 8 hours. Supposing somebody drives 101 miles. What's the estimated time? And the estimated time is this. So driving that additional mile takes how long? An extra how much more time? It's going to be the difference between this figure and this figure. 0.678, which is exactly this figure in here. So can you see what the slope is? The slope says for each additional mile you drive, the slope tells you how much additional time it's going to take you, which is 0.67, and that's what this is giving us. And if we were to put in 102 miles, what's the time to drive 102 miles? The estimated time is going to be this figure. So what's the increase from driving 101 to 102 miles? What's the increase in time? It's going to go from 812 to 819. So what's the difference between those figures? And the difference again is 0.67826. It's the same figure, which is what linear is. Linear means you get a constant change for each additional mile. It tells you that you're going to in this case, drive an additional 0.67 of an hour. And by the way, what is 0.67 of an hour? Well, let's see. So 0.67 of an hour is, in terms of minutes, 4 minutes. So for each additional mile, it's going to take an additional 4 minutes. And we also said that R squared, telling us how good the model is 66%. So what I can do is actually say on this scale, remember the scale for R. So this is the scale for R, goes from 0 to 1. And R's 50% is about here, 66% is, I don't know, it's around, I don't know, somewhere here. So it's telling you how close you are to the model being perfect, as opposed to being no good as you move back towards 0. So and the 66% is also telling me that there's other factors that account for 34% of your time it takes you to actually make your deliveries, which are not being picked up in this model. So let's actually move on back to the PowerPoints, because the PowerPoints just then say to us as well, it says, you know, what we want to do now is take into account the possibility of bringing in another factor that influences how much time it takes for you to actually complete your task, complete your assignment, your driving assignment. And what they're going to look at is that not only the distance you've traveled, but also the number of deliveries you've made. So they think that may be an impact. If that is an impact, which it probably is, but if that is an impact, we should see a model which has an R squared value, which moves further towards 1 than it currently is, if it's a valid factor. So that's what we're going to look at here. And what we can do here is open up the Butler example. So we've got Butler spreadsheet, Butler with deliveries, and that's a spreadsheet right there. So they actually work on that spreadsheet. So what is your dependent variable again? Your dependent variable again is time, because time is going to be dependent on, call that Y. Time is going to be dependent on how many miles you drive, and that's going to be one of your independent factors. So why don't I call that X1? And then it's also going to be dependent on the number of deliveries you make. So the amount of time it takes you to make your deliveries is going to be dependent on two independent variables: how many miles you drive and how many deliveries you make. And what we can do now is we can run the regression on this again. You do it using exactly the same keys as we had before. If your Excel is playing up on you, you have to hit data, and hopefully data analysis comes up over there. Showed you in an earlier video how to add data analysis in if you don't have it, but pretty much if it's on a Mac, you're just going to go to Tools, go down to Add-ins down here, Excel Add-ins, and then you're going to make sure that Analysis Tool Pack is checkmarked. Okay, so how are we going to do this? We're going to go into Data Analysis, we'll go to Regression. It's the same regression as we used for linear regression in the previous example I was just working on a moment ago. So let's actually get rid of these things that I've stayed in from before. And so what's our Y range? This is my Y range. And I'm going to press Control Shift and down. And well, sometimes it works and sometimes it doesn't with these Macs, but there you go. Let's put all this in here. There you go. So that's my Y. And my X range, how do I put my X range in? Well, the way I put my X range in, you don't put them in individually, you put all your X's in together. So we've got two X's here, and there you go. And where should we put the output? In cell E1, seems fine, press OK. And if we go up to cell E1, our output should be there. There you go. So this is actually giving us a multiple regression model. A multiple regression model is simply a model that has more than one independent variable. It doesn't just look at mileage impacting on how long it takes for you to complete your deliveries. It's now looking at two factors. One of them is mileage and the additional factor of number of deliveries. So this is a multiple regression model. We could look at a third factor and a fourth factor and a fifth factor. That will also be a multiple regression model. A multiple regression model has more than one independent variable or more than one thing driving the dependent variable. So this model will be classified as a multiple regression model. The general form of this model, let's go on here. The general form of this model, do it up here, is going to be that y hat equals b0 plus b1x. That would be linear, but now it's multiple b2 x2. It's got two independent variables here and here, and those variables correspond to, as we could see up here, they correspond to miles, and they also correspond, and also deliveries. So that's miles, this one is miles, and this one's deliveries. And it's fairly simple to actually write out the model in full. So that hat up here means estimated. So estimated and y, we said that y was the time. So the estimated time to complete your deliveries is equal to b0, which is the intercept, which is 0.12. I'm getting it from here. 0.12733 plus b1, which is, I'm getting that from the next cell down, 0.067182, and that's going to be multiplied by x1, and x1 is miles, so multiplied by the number of miles, and then we're going to add in 0.68999 times the number of deliveries. So let's put the deliveries. Okay, and that's our multiple regression model. So if you have a driver, you tell me how many miles they're going to drive, and you also tell me, so the miles they're going to drive, and you tell me how many deliveries they're going to make, I can just pop the miles and deliveries into this formula, and out on the other side over here is going to pop the estimated time it will take to make those deliveries. So let's actually have a look at an example of that in action. So let's do estimated time. The estimated time for somebody to make a certain number of deliveries and a certain number of miles. So that's the miles. They're going to have so many miles, and these are going to be the number of deliveries they're going to make. So we can actually work all that out. So let's suppose that somebody's going to drive 100 miles and make 5 deliveries. Okay. So how are we going to work out the estimated time? Well, I'm just going to put 100 in for miles and 5 in for deliveries. I'm going to get Excel to do the work for me. So I'm going to say it's going to be the intercept, press it, F4, plus the slope times, and the slope in our case is going to be multiplied by, let's see, it's not going to move up for us. I'm just going to put that. I'm going to have to amend the formula because in a second, and we're going to have to add in here. You may notice that Excel's playing up on me. I'll leave it in here rather than correct this, just in case it plays up for you, so we can correct the formula. You can see that it shouldn't be referring to G23 and H23. Excel wouldn't let me move the cells up. So what I can do to amend that formula is actually I can click on that and drag it up like that. And I can click on this and drag it up. It's very temperamental, is Excel. Okay, that's the correct formula. So there you go. That's the correct formula. It should be. Okay, and that's the answer. So someone driving 100 miles, making 5 deliveries, I expect it to take them 10.25 hours. Now, let's consider this. Supposing somebody's going to drive 100 miles and make 6 deliveries. What do you think the additional time is going to be to make that additional delivery? Well, let's calculate it. Let's figure out what it's going to be. That's the amount of time. So what's the additional time? It's going to be the difference between this and this. That's the additional time. So the additional time is 0.689, which happens to be this figure in here. So what does that mean? That means that the slope here for deliveries says that for each additional delivery you make, see, we made one additional delivery, but keeping the miles constant, keeping everything else constant. So for each additional delivery you're going to make, keeping the miles constant, it's going to take an extra 0.689 of an hour. And you can do that again. You say, okay, does that always work? Yeah, it does. If I'm going to make 100, I'm going to drive 100 miles and I'm going to make 7 deliveries, how long does it take to make that additional delivery? Well, total time is going to be that. So what's the difference? What's the additional time? It's going from 6 deliveries to 7. It's going to be this minus this, which again is going to be the same figure. So that's what the slope means here. How about this? Let's consider this. Supposing you are going to drive 100 miles and you're going to make 5 deliveries, and someone else is going to drive 101 miles and also make 5 deliveries. So the difference here is that I'm holding the deliveries constant, but I'm increasing the miles. So these two people are going to make exactly the same amount of deliveries. But the only thing that differs between them is the actual miles driven. So how long does it take to drive that additional mile, given that you're making the same amount of deliveries? Well, let's see. Let me just copy the formulas down. So what's the additional time? Going from 100 to 101 miles, and that's just going to be equal to this minus this. And what do you think it's going to be? 0.067. It's this figure in here. So the 0.67 says for each additional mile you drive, keeping everything else, i.e. the deliveries constant, it will take you an extra 6.7 of an hour. And we can do it again if you want. So what happens if you drive 102 miles, but you're still making 5 deliveries? What's going to happen then? You can see, oh, well, look, this is what it's going to, how long it's going to take. Okay, so what's the increase in the time? Well, the increase in the time is going to be the difference between this and this. Same figure. So hopefully that gives you an understanding of what these coefficients up here actually mean. It's very useful to understand that, and it kind of does make sense. And the other thing that I'd like to point out whilst we're on this section is that the slope, the R-squared coefficient of determination is 81%. So what was it previously? It was like 66%. And now we've added in deliveries to the equation. What's happened? Our R-squared has increased quite substantially. So what we've in fact done by improving our model, by adding in deliveries, which obviously is an important factor, on our scale for R-squared, the coefficient of determination, we've gone from 66% where we were before, and we've gone up to 81.7, let's say about 82%. So this model's a lot better. It's getting closer to 1 to giving us a really nice model. So the other thing I'd like to look at, which is in your PowerPoints, is the PowerPoints here just show you how to do the regression which we've just carried out. They're the results, which is the same as the results that we got. And this point here is just mentioning that the model is not a perfect fit. The model doesn't perfectly fit your data. We already know that. If the model perfectly fit our data, R-squared, coefficient of determination, would be 1 or 100%. So it doesn't exactly replicate the data, but it's fairly close. So a couple of things I'd like to point out here. Before, when we were looking at the linear regression model, we were basically fitting a straight line. We had data points and we're fitting a straight line to it. But that's when we had one independent variable. Now we have 2 independent variables, so we move into 3D space. So rather than getting a line like this, we're actually getting this plane in 3D space. And the other thing is, what it's pointing out here is that all the actual data is actually scattered around. And this is my estimate, just as the straight line is my estimate of all the data, of the data. It's my model. The estimate when you have a plane is this thing over here. It's just a whole, when you have 2 dimensions, you have a plane. So it's just saying that for the 7th assignment, the actual figure, the actual amount of time it took the person for the 7th assignment is that, but the model estimates what's on the plane, and they're not all the same. There is residual effect coming through there as well. Moving on. Inference and regression. So let's look at the conditions necessary for inference and regression. And let's move on from here on to the next slide. What is statistical inference? Do you remember what statistical inference is from an earlier course? Statistical inference is basically when we want to find out something about the population, say, and so, for example, supposing this is my population, I want to find out what the population mean is. I don't have enough information to do so, so I'm going to choose a sample, work out the sample mean, and whatever the sample mean is, which I can work out fairly quickly and easily, I'm going to use that as an estimate of the population mean. That's inferential statistics. And when it comes to regression, what we're going to be estimating in the same way is these guys in here. These are population coefficients, and just as the population mean, it's very difficult to actually calculate them if you don't have all the information. So what we're going to do is actually use samples and work out sample coefficients. So instead of beta 0, we use B0, and then we're going to use B1 instead of beta 1, and so on. So that's what the inference is about here. And what are the conditions necessary that we require for us to be able to use everything we've learned so far, and to be able to also use Excel regression analysis to be able to solve everything? What are those conditions for the residuals? So we've got certain conditions that must apply for the residuals. And what are the conditions for the residuals? Well, one, the residuals are the error terms as well. Okay, so one is that they must be normally distributed. Two, the average of all the residuals must be equal to 0, so the mean is 0. 3, the variance at any point is constant or approximately constant, and the residuals must be independent. So these are the conditions that must hold for us to be able to use all the theory that is backing this. So how can we tell that? Well, let's look at a few examples. Before we look at a few examples, let's try and look at this in action, a schematic of it. So you can see here what they've tried to do is they're trying to show us that they're using a linear regression example. This is your straight line going back down there. And basically they're trying to show us here that we have a normal distribution. So the residuals above the line and below the line are normally distributed, which means they're going to get a lot more of them closer to the line and less fewer as you move away. It means that they're centered around the line. It means it seems to be showing us that the variations is constant, and basically the things that we saw before, the average is 0, so you're going to get an equal amount below the line as you do above the line. And that's pretty much it. It's difficult to show independence. Independence may be violated sometimes, but that's just a graphic. So normally distributed, average is 0, equal amount above and below the line, and the spread at any point is about the same. So that's the schematic of it. Let's look at a further schematic and see if we actually had an actual example and we plotted the residuals, what they would look like. If this is what our residuals look like, what would you say? Would you say that it appears that we have the conditions not being violated for us to be able to use this regression analysis? So remember the conditions that we just spoke about are normal distribution, mean 0, equal variance, and independence. So overall, what I can see here is the variability is approximately the same all the way along. So between here and here, the variability is about the same all the way along. there doesn't seem to be any curvature or anything to make me think that there's a possibility that we don't have linear data. So remember, these are plots of the residuals. Now, if the residuals, by the way, don't meet the conditions, what can you do? What's the next steps? Well, it could mean that you've omitted an important independent variable. So there's something really important from the model that you've missed out. Or it could mean that the functional form of your model is inadequate. Basically, your model is wrong. So your model is going to be wrong in some way. There's things that it could possibly mean. Let's look at some more examples here. So if these were the residuals to some analysis I was doing, would I conclude that my conditions were violated or not violated? Well, this first one right here, I would say that the variance is increasing. Look, the variance is increasing. It's small, it's larger and larger and larger and larger. And one of the conditions is that we need constant variance or equal variance throughout, and that condition is violated. So if these were my residuals, I would say that the conditions are violated and the model's no good. How about this second one over here? What would I say about this second one over here? Just point to it, put an arrow towards it. There seems to be a systematic curvature, and so it doesn't seem that the data is going to be linear right here. How about this one down here? So I'll put an X by that one as well. That one doesn't look good. That violates our conditions. How about this one down here, this third one? It doesn't appear that the data is symmetrically distributed. It's very closely bunched here and more spread out over here. So that the data doesn't seem symmetrically distributed as you would expect for a normal distribution. So that falls through as well. Now this fourth example over here is looking at when you have data plotted over time, some sort of time series, and you should put your residual plots in terms of time as well. And it does appear here that, you know, the residuals go, they're low, then they're high, then they're low, then they're high, then they're low, then they're high. Something funny is going on. It probably means that the time effect has not been properly included in your actual regression model. So again, this one would be a fail. Okay, let's move on. How about here? This is the Butler trucking example. And when we look at the Butler trucking example, the residuals here, they look good as well, don't they? They look very good. There seems to be the variability being about the same all the way along. So all the way along, the variability seems about the same. There's nothing to indicate that we don't have normality here. So again, this one I would actually agree with, say it's giving me good indication that our conditions to use regressions have not been violated. The multiple regression models that we're looking at are in fact multiple linear regression models. Let's take a look at the next slide. And as such, they require us to ensure that each individual independent random variable is linearly related to the dependent variable in its own right. So what does all that mean? So the models we're looking at, or this particular model, has the form like this: b0 plus b1 x1 plus b2 x2. So this is a multiple regression model because it has multiple or more than one independent variable x. It's got a couple of them. And but we want it to be a multiple linear regression model. What that means is when I split the model out to look like this, when I just consider x1 on its own, I need this to be a linear regression model, and I also need this to be a linear regression model. So when I cut this out and just look at this, I need this to be a linear regression model. And then after, when I cut this out and bring this back in, I need them to be linearly related. So that's what we want to do. Now to test this, we can actually use a test that we've seen before in earlier stats courses. We want to test to see if the slope for coefficient 1 is equal to 0. If it is equal to 0, if there's no slope, that means implies there's no linear relationship. And when does that happen? That happens when alpha is smaller than the p-value. On the other hand, if the outcome of our hypothesis test that we're going to run is going to be that the slope does not equal to 0, that implies that there is a linear relationship. And that's going to occur when alpha is greater than or equal to the p-value. Now, on the next slide, that they show you how to use the critical value approach. I prefer to use the p-value approach because it's faster. So what I'm going to do for this is I'm going to go back over to let's go back over to our Excel spreadsheet that we had for this. So this is the Excel spreadsheet that we had. And it's pretty cool because we can actually find the p-values for, let's go into here. And we can find the drawer off. So we can find the p-values for the miles and the delivery. So this is the p-value for miles, and below is the p-value for deliveries. The p-values are right in here. Let's go over here. These are the p-values for miles and deliveries respectively. Now, these are very, very small numbers. What does 3.5 e to the negative 83 mean? That actually means that we need to move that decimal point in the negative direction by 83 spaces. And 2.85 e to the minus 69, we have to take this decimal point and move it in the negative direction, which is that way, by 69 places. These are extremely small numbers. If you're not sure how to do that, you can just click on them and you can just go up to the formatting and you can just change the formatting to number. And you can see there's 0, and you can add some decimal places and you can see they're pretty much 0. So the p-values are approximately 0 for both miles and deliveries. So if we go back to our test that we've got here on this spreadsheet, if we take any reasonable value of alpha, like 5%, alpha, 5% will be definitely greater than or equal to 0. So that means that we do have a linear relationship both for the actual miles and the number of deliveries. So we can actually test that quite simply. Let's look what we have on the next slide. Now, on the next slide, it says, look, you could have used the critical value approach. And when you use the critical value approach, you have to work out the test statistic. And again, if we go back to the Excel sheet, the actual test statistic is actually given to us. It's right in here. They're the test statistics for the miles and the deliveries respectively. And just by the by, so you know, if we take this number and divide it by this one, I get this one. And this one divided by this one, I get this one. And that's what it's basically telling you in the notes. So we can just try that out. So if I say it's going to be this number divided by this one, it's actually going to give you the one above. Okay, so there we have that. So the next part is there's another way we could have actually run this test to figure out if the coefficients are 0 or not equal to 0. And the way that we run that test is simply to see if the confidence interval for that coefficient contains 0 or does not contain 0. If it contains 0, then we say there's a good chance that the value is in fact 0. So it's a similar test that we were doing before. So again, if I go over to this Excel output, I've got right here, I have the confidence interval for the miles driven. And the confidence interval goes from 0.6 to 0.7. It does not contain 0, which probably means that the coefficient is not 0. So it's a similar test that we did before where we're using the hypotheses test. It's a similar way of looking at it. And that's the result we got before, that the slope does not equal 0. When we ran the hypotheses test and used the p-value approach, that's what we got. How about deliveries? Does that appear to possibly have a slope of 0? And if it has a slope of 0, it means there's no linear relationship. The answer is no, because you can see right here, the confidence interval for deliveries does not contain 0. So the chances that the actual coefficient is 0 is very, very unlikely. So that's another way of actually conducting this, these tests, a different way of conducting those same tests. So what should we do if our statistical analysis that we just ran tells us we should actually remove one of the independent variables from the model. Supposing it says we should have removed the miles traveled from the model. So what do we do then? Well, if you know that based on your practical experience that that particular element that statistically you should be rejecting, according to the statistical test, should really remain in the model because it's relevant, keep it in the model. It's very practical. On the other hand, if the model works well without it, then take it out. But whatever happens, when you have this issue where an independent variable is said to be non-significant, remember, non-significant means that it's not related, it's not significant, it's not related. And I'll tell you why that is. Let me just go back a bit. It's non-significant or not related because the null hypothesis in here is no linear relationship. And we kind of assume that the null hypothesis is true until we can prove it's not. So non-significant means we don't deviate from the null hypothesis. So what can we do in that case? When it's non-significant is basically up to you as an experienced user of statistics. You should be able to figure that out, but you're going to need special consideration to be able to do that. So let's look at another example here, and this example is going to be based on multi-collinearity. Now, multi-collinearity is a problem, or can be a problem, because two of your independent variables may be related to each other. So let's move on to an example. And if you actually look at your Excel data sets that you'll be given one which is called Butler with gas consumption. So this is the same thing that we've been looking at already. It's the same company. We've got the time, the number of deliveries, and gasoline consumption, and the miles traveled by each of about, well, a load of maybe 300 different assignments or 300 different drivers. Yep, we've got about 300 different drivers there. So for each of those drivers, we're actually told, for each of those assignments, we're told the miles traveled, we're told the gasoline consumption, the deliveries, and time. Up until now, we didn't have gasoline consumption. So again, for this particular question, time is going to be the dependent variable. I'm going to call it y, and we have three independent variables now. So we've got x1, and we've got for miles is x1, and then we've got x2 is going to be gasoline consumption, and x3, another independent variable that may drive how long it takes you to complete your assignment. We're going to call that x3, number of deliveries. So as I said, we already had miles and deliveries already, but we didn't have gasoline consumption. Let's have a look at the model and let's run a regression analysis on it. So let's go into data analysis, regression again, and our y range is just going to be all this. And our x range is just going to be put in all together. All our x is going to be put in together. So this is our x is here, go all the way down. Make sure that labels is clicked because we have included labels in this area that I am highlighting now. There you go. So labels is clicked. And let's put H1. Where do we want the output to go? Is H1 good? Yeah, H1 seems good. Let's put it in H1. And we're going to get these results. So what's this telling us? We can look here to see what our linear regression model is telling us to do, or what it's recommending to us. And so put those values in now. So what does our model look like? Our model looks something like this. It's going to be that y hat equals b0 plus b1 x1 plus b2 x2 plus b3 x3. And we can fill that in. So that hat on top, this guy in here is just the estimated, and y is going to be the estimated time, equals b0, which is 0.23. I'm just going to cut down 0.24. I'll just round to 2 decimal places. That's going to be B0. And then B1 is going to be, I'm reading these from the green area. It's going to be 0.08 times x1. Now x1, if you look at the top left of the sheet, that's going to be the miles traveled. And then we're going to add in, in fact, we're going to subtract here. So you can subtract. Okay, just move that to there. And we're actually subtracting here. And we're going to be subtracting 0.12. I'm only doing it to 2 decimal places to save some time. Time times the gasoline consumption. And then we're going to add in the third one, which is 0.69. And that's going to be multiplied by the number of deliveries. And that's what your model is. That's how you can actually work out the estimated time. So if somebody comes along and says, somebody drove 50 miles and they used so much gasoline and they made 7 deliveries, then you can actually calculate what the estimated time for them to complete their assignment. Now, before we can actually use that, we have to use what we've looked at earlier. And what we looked at earlier is checking to see if all these independent variables really are linearly related to the dependent variable. And we can use the test that we spoke about earlier to see if these guys are linearly related. So if you remember what the test was, I'll just do it up in the top right. We actually said something like, we said that if beta 1 or beta I generally is equal to 0, that means there's no linear relationship, and that occurs when alpha is less than the p-value. And if the slope or the coefficient does not equal 0, that means there is a linear relationship, and that occurs when alpha is greater than or equal to p. So when we actually look at the p-values in here, and we look at the p-values for miles, that's a very small number. And also for deliveries, it's a very small number. So that means that when the p-values are small, if we just take any value of alpha, say 5% is a typical value, 5% will be greater than both, 5% will be greater than both this figure and this figure. Remember, these figures are very small. That figure is very small and that figure is very small because you know that e to the minus 18 means you take this decimal point and you make it move 18 spaces in this direction. And so if you want with those figures, what you can do is just go into the formatting and change it to number format, and you can see that they're approximately 0. You can add some more decimal places, it's still 0. So you can see here, you can see how small these values are in here. So that's going to be approximately 0 as well. So what does that mean? That means that the miles and the deliveries should be kept in the model, but it also means that gasoline should not be kept in the model, because if alpha is 5% and the p-value is 19% and the p-value is greater over here, the p-value is greater than alpha, 19% will be greater than 5%. Remember, I made the 5% up, but it's a typical value. So that means there's no linear relationship, and that means we should remove that from the model. But sometimes this is confusing and misleading. Gasoline should be related to the, really should be related to the time, because gasoline dictates how many miles you do. The more gasoline you use, typically the more miles you're going to do, and the more miles you do, the more time. So it should be related. So why is our statistical test telling us to actually reject it? Well, in short, the basic answer to that is that gasoline consumption and miles traveled are both counting the same thing. It's the same aspect that they're looking at. So this model's kind of saying we don't need to use gasoline consumption because miles traveled is kind of giving us the same type of information. And this is an example of the two variables, which are miles traveled and gasoline consumption, being closely correlated. Let's work out the correlation for them. Let's do equals correl. So the correlation coefficient between miles traveled, which is going to be this, and gasoline consumption. Let's go up to the top. What do we get? What value do you get? 95%. They're very closely correlated. They're very closely related. They're measuring the same thing. So we have to keep an eye for this. The PowerPoints, if we just go back to the PowerPoints, they actually say that multicollinearity is basically when the independent variables, like in our case, gasoline and mileage traveled, are actually closely related. And that's what multicollinearity is. And the general rule is that if the correlation between them, in our case, it was very high, wasn't it? In our case, it was like 95% in here. If the correlation is 70% or above, then you have to take action. You can't include both of those variables because they're both counting the same thing. Large samples. What can we do with large samples? Do we have any issues with large samples? And the answer is yes, we do. The methods that we actually use to calculate regression analysis actually rely on finding variability in your data. When you have large samples, you can't spot variability, and the variability disappears. And so the results you're going to get when you've got really large samples are always going to be significant. They're always going to tell you, keep all the independent random variables. They're all good. They're all valid. So let's look at an example of this. So this is an example of like 5,000 people. So that's a kind of a large sample. And we're looking at how much they spend on their credit cards. And that's the dependent variable here. And the assumption is that it's based on their annual income. Probably the more income you earn, the more you spend on your credit card. The size of your household, the more people in your household, the more you're going to spend, presumably. The years of post-high school education, so I'm not sure which way that's going to go. Post-high school education, the more education you have, then the more money you're likely to earn. But you're also likely to be more careful about how you spend your money because you're more aware, perhaps. And the hours per week watching television, not so sure if that really is related to how much you spend on your credit card. Maybe it is. Maybe you're watching some channel, you're seeing ads going on, and then you start buying stuff. I'm not sure if it is. But let's run a regression analysis on it. So let's hit data analysis, and regression. And the information is there. Just put the information in. Let's run it, see what we get. And there you go. So let's see what we get. And we can look at the p-values. So let's go over here, and we can go to the p-values. And what do we get? So do you remember the test we were talking about? The same old test to see if we should keep each of these independent variables in the model or not. We're going to keep them. What the test we were going to do, if you remember the test, let's just draw it in again. We're going to test to see if the slope beta 1 is equal to 0, and that means that there's no linear relationship, and that is going to occur when alpha is less than the p-value. And when the slope does not equal 0, that implies that there is a linear relationship, and that happens when alpha is greater than or equal to the p-value. So if we look at these in here, I think you'd agree that they're all very small numbers, okay? And again, if you're not sure how you do that, just go to the format, change the format to number, and you can see they're all approximately 0. You can add a few more decimal places by moving up here. They're all approximately 0. So we can see that any reasonable value of alpha would be given, say 5%. 5% will be great, 0.05 will be greater than all of those. So that implies that we've got this scenario here, that the alpha 5% will be greater than or equal to 0, which means that there is a linear relationship. And it could be that we don't have a linear relationship with the hours spent watching television, but because we've got such a large sample size, that is going to always lead us to believe that all the independent variables in there are in fact valid, as this case does here. There's another test that you can actually do to figure out if the model overall is valid. So here we look, using the p-value, we're looking at individual items, individual independent variables. Is annual income valid? Yes. Is household size valid? Yes. Is years of post-high school education valid? Yes. And hours per week, is that valid? Yes, according to this model, which is large and we know may be flawed. But is there another test that we can do where we can just test the whole model? Rather than testing individual parts of it, can we test the whole model in one fell swoop? And the answer is yes, there is. And if you've covered ANOVA before, you may remember this. You can actually check to see if the coefficients, let's go on to draw. You can check to see if the coefficients, so I'll do it here, if the coefficients beta 1 equals beta 2 equals beta 3, dot, 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 how many coefficients you've got. You can check to see if they're equal to 0, or you can check to see if at least 1 is not 0, at least 1 not 0. And this will be your null hypothesis. I didn't want to put the hypothesis symbols in. I don't want to remind you of any nightmares you might have had with the hypothesis stuff. The first one's the null, the second one's the alternative. And if the null hypothesis, if we're going to say do not reject it, that occurs when alpha is smaller than the p-value, and we'll reject it when alpha is greater than or equal to the p-value. So in this particular case, the p-value in question, when you're checking everything in one go, is given a special name, and it's called significance f, and the p-value is a significance value, but it's called significance f because the guy that came out with it, his name was Fisher, Sir Ronald Fisher, and he, in fact, in honor of him, they actually call it significance f. So in this case, significance f is equal to 0. So again, any reasonable value of alpha, say 5%, will be greater than 0. So that means that at least one of the betas is not equal to 0. So that means the model is valid. If we'd got a do not reject H0 up here, that means that all your coefficients are equal to 0. So if everything's equal to 0, your model is worthless. So your model is only going to have some validity if everything's not equal to 0, if all your coefficients are not equal to 0. It doesn't mean that your model is brilliant or it's fantastic. It just means you can use it. Overall, the model works. There may be parts of it that don't happen to work, but overall, you can use it. So let's move back to the PowerPoints. That's a note about large samples. And this is using the significance f that we just used, and this is how you actually calculate significance f, but as you saw, it was 0 for us, and you don't actually have to calculate it yourself. It's going to be this value that's given to you in here. You don't have to calculate it yourself. Moving on. Categorical independent variables. So what are categorical independent variables? The previous independent variables we have considered, such as miles traveled and number of deliveries, have been quantitative numbers. But the new variable that we want to look at in this section is going to be rush hour traffic. We're going to add in rush hour traffic to the equation that we're actually going to use. This variable, because it's not a number, is called a dummy variable. And that's what we're going to look at. And it's telling us more specifically here that the dependent variable y travel time and the independent variable, so we're going to be looking at, and I'll show you the information in a second. We're going to look at miles traveled, and we're going to look at the number of deliveries made, and we're also going to look at rush hour traffic. So we're going to give a 0 assignment if a particular driver did not drive in rush hour traffic on the freeway, and if they did drive in rush hour traffic on the freeway, we're going to give that a rating of 1. Okay, so we'll do that in a second, but before we do that, we'll look at the next slide, and the next slide is actually looking at the residuals. And let's remind ourselves what the residuals are in this case. The residuals are going to be, call it E, and they're going to be yi minus y hat. What that actually means is going to be the residuals are what actually happened, what we observed. So let's put what we observed minus what the model is saying. That's what the residuals are for us. So you can see here, for this first situation here, these are drivers that actually drove in rush hour traffic. Now, what we're actually looking at here is the model as it stands. We haven't added in this factor of rush hour traffic. We're saying the time it takes you to make your deliveries is based purely on the number of deliveries you make and the number of miles you drive, and that's it. And when we do that, what does our model look like? What do the residuals look like? Well, if we say, well, how about all these drivers over here? These guys actually drove in rush hour traffic, and all the residuals tend to be positive residuals. So a positive residual, a positive value to this, means that your observed is greater than what your model predicts, that your model is under predicting. So for the drivers that drive on the freeway, the model is under predicting. How about over here, the guys that do not drive on the freeway in rush hour traffic? Our residuals here are negative. They're this way. They tend to be negative. And so if this value in here is negative, that means the model is larger than the observed. So that means that the model is over-predicting the time it takes for those that don't drive on the freeway. That kind of makes sense, because when we don't take into account the freeway and we just average out everybody's time, irrespective of whether they drove on the freeway or not, in rush hour traffic, the model is just going to take an average position. So the guys that don't drive on the freeway, they're going to be less than the average, and the guys that actually do drive on the freeway in rush hour traffic, they'll be higher than average. And so these results suggest that the dummy variable could potentially explain a substantial proportion of the variance or variation in travel time that is unexplained by the model, not including the rush hour traffic. And so we're going to proceed by adding the dummy variable to the current Butler trucking multiple regression model. And what we're actually going to see, I'll show you on the next slide. I'll actually go over to the Excel. And this is the Excel. And you can see now we've got the time it takes to complete an assignment, how many miles they drove, the number of deliveries, and whether or not they drive in the freeway. Remember, 0 means no freeway traffic driving, and 1 means yes, there was freeway traffic driving. And if we run an analysis on that, data analysis, regression, and I'll put the stuff in there and press OK, and this is what we're going to get. So these are the things that we're kind of interested in down here, the coefficients down here. And let's do the coefficients in. So that actually gives us a new model. And what does this model actually mean? And we can actually write the model in as well and see what it means as well. But it's going to be, let's write in, I'm just going to draw. So what it means is we've got y hat equals b0 plus b1 x1 plus b2 x2 plus b3 x3. That hat means estimated, so this is the estimated time to complete your assignment, equals your intercept, which is a negative value, is possible, 0.3. I'm only going to take the first decimal place this time, plus the miles coefficient, which is 0.07 times miles, plus 0.7 times. So I'm actually just taking these figures from in here and I'm actually just rounding them to 1 decimal place times the number of deliveries you make, and plus finally 0.99. I'm going to put 1. I'm just going to put 1 there. It's approximately 1. And so I'm just going to put plus 1 times rush hour traffic. So if you're driving in rush hour traffic, that's going to be 1. And if you're not, that's going to be a 0. So that's the model that we actually come up with. And let's just do something. We've done this before on a previous example, but I'm going to do it here again. So what does specifically, what does this 0.0672 mean? Let me just get rid of this. So what does this figure mean in here? So that says, for each additional mile that a driver drives, holding the number of deliveries and whether or not they drive on the highway constant. So don't change that. So if we hold those constant and the miles, an additional mile is driven, that will add 0.672 hours, which is about just over 4 minutes, to the time it takes them to complete their assignment. What does the figure below that 0.67 mean for deliveries? It says, for each additional delivery a driver makes, but holding the miles they drive the same and the height, whether they drive on the highway or not, keep that the same, don't change that. But they make an additional delivery. That additional delivery is going to take another 0.67 of an hour. And what does this third one mean in here? This is saying, okay, if we, for a driver driving the same amount of miles and making the same deliveries, if they drive on the highway, that would add about another additional hour to their drive. So that's the way that you interpret those. It's the same as same interpretation as we actually went through before. Let's go back to the PowerPoint to see if there's anything that we can look at here. So this is the Excel spreadsheet that a copy of it that I just came up with. And this is explaining what the 0.672, the 0.6735, and the 0.998 all mean. Oh, it's also telling us about R squared here. R squared is telling you about how good the model is. And can you see how the model's increased? It started off at 66%, and now it's up to 88.4%, the coefficient of determination R squared. So that actually is up here, right there. You can see the coefficient of determination in here. So that's pretty good. That's telling us how good the model is. There's not many more factors we could have actually taken into account to help us better predict the actual time it takes to complete an assignment. That figure is actually very good. And this is just a note on categorical independent variables, showing you again the just how the numerical side of it, the actual equation side of it looks. And you can see this is an equation, it has betas in it, which is population data. And it's just saying that right here, if somebody's driving in rush hour traffic, this value is going to be a 1. And if they're not driving in rush hour traffic, that value is actually going to turn out to be a 0. And here's some examples here. It's saying if somebody, this is the main equation, and if somebody is not driving in rush hour traffic, which means x3 equals 0, this is what the equation looks like. And if someone is driving in rush hour traffic, you put x3 equals to 1, and this is what your equation is going to look like. So let me just come back here. And so that's pretty much it for this particular example. And I'll just move on to the next section. So let's move on. So let's look at a more complex example of categorical variables. Now, a general rule is the number of categories you have is k. And the number of independent variables you need to add to your model to be able to cope with those is k minus 1. So in the example we looked at just now, we had you either drive on the freeway in traffic or you don't. And so there are 2 different levels, and k equals 2 in that case. But the number of independent variables I need to add to my model to take care of that is 2 minus 1, which is just 1. And that's exactly what we did. If we go back to the model, you can see that highway was the only other independent variable we added in. There may be zeros and ones going in it, but highway was the only one we added in. So even though we had two different levels, you drive in traffic or you don't, we only actually had one additional independent variable. Generally speaking, you have k different levels, then you have k minus 1 independent dummy variables that you have to add to your model. There's an example here. So we've got manufacturer of vending machines organize the sales territories for a particular state into 3 regions, A, B, and C. So we can think of it as California, and Northern California is A, Central California is B, and Southern California is C. The managers want to use regression analysis to help predict the number of vending machines sold per week. Okay, suppose the managers believe sales region is one of the important factors in predicting the number of units sold. How many independent variables, dummy variables, would I have to add in to cope with these 3 different regions? Well, remember, 3 different regions, k equals 3, and the rule is k minus 1 is what dummy variables would need to be added, so 3 minus 1 is 2. And that seems a bit strange, but it's correct. So the way we do that, the 2 independent variables, or 2 dummy variables we're going to add in are going to be x1 and x2. And so how's that going to work? Well, x1 will be given the value 1 if you're in sales region B. It's going to be given the value 0 otherwise. x2 will be given the value 1 if you're in sales region C, or 0 otherwise. So this takes care of region B and region C. What about region A? Well, what happens when I'm not in region B and I'm not in region C? What does that mean? It means I've got to be in region A. So when I'm in region A, x1 is going to be 0, I'm not in region B, and x2 is going to be 0, I'm not in region C. So I'm not in region A, I'm not in region C. By default, I must be in region A. When I'm in region B, we already know that I put 1 for region B and a 0 for C. And when I'm in region C, I'm going to put a 0 for x1 because it means I'm not in region B. But yes, I am in region C, so I'm going to put a 1 in there. So it may seem a little bit difficult to start off with, but after you've done a few examples, it seems to fit into place. And let's see how that would look in action. And so what we see here is this is the general equation in there. And so what do we have? We have here the general equation. Supposing I am in, if x1 equals 0 and x2 equals 0 as well, that means I'm in region A. So all I have to do is come into this equation and put x2 equals 0 and x1 equals 0. And that's going to say when I'm in region A, then my equation that I used to predict is just beta 0 because these guys just disappeared. And likewise, when I'm in, you can see how it moves on down here. So when x1 is 0 and x2 is equal to 1, that means I'm in region C. So when I'm in region C, I just put x1 equals 0 in this equation up here. So I'm going to put this guy equals 0, but x2 is still valid, and I end up getting this equation down here. Okay, so it just takes a little bit of getting used to. And basically what this means is here is that the default region is region A. Beta 0, this corresponds to the mean or the expected value of sales in region A. And then beta 1 is the difference between the mean number of units sold in region B and the mean number of units sold in region C. So basically, the beta 1 is saying, what is it that I have to add to region A sales or subtract to get to region B sales? And likewise for region C, beta 2 is the difference between the mean number of units sold in region C and the mean number of units sold in region A. So you can see that beta 2 now is what you have to add or subtract from region A sales to get to region C's sales. Just takes a little bit of getting used to.